Hello. Good day, everyone. My name is Jet. To my esteemed panelists, Ma'am Ray, Sir Ed, Sir Ricky, and also to my dear advisors, Doc James. Welcome to my defense presentation. Took me a little while to finish this as I juggle work and studies, but finally here we are. Um, for this presentation, this would be for the final defense of my topic, assessment of the performance of an outdoor scroll condensing unit with digital modulation capacity control for retail refrigeration. So here are the parts of the presentation. For the significance of the study, basically, this would provide insights on the operation of the unit, also quantitative evidence on the performance of digital modulation on real-world application, especially that we have operated this study on an actual retail store in the United States. And this research would also benefit retail establishments that use this kind of technology, especially refrigeration, looking to improve the efficiency of their system. And also, it would give insights on how digital modulation as a method of capacity control. Here are the objectives. Basically, the objectives are to monitor and gather the data. This was done through data extraction and data analysis, and then assessment of the system's capability to maintain precise temperature control. This was done through numerical and graphical analysis of the data, and also the evaluation of the effect of different operating conditions, such as ambient temperature on different seasons. So different parameters that are used on this study would be analyzed using multiple linear regression, statistical analysis technique. And also estimation of the energy efficiency of the outdoor scroll condensing unit. So this was done with the tool template used for the study, which would be shown later on the slide. So a quick refresh on the methodology. This is a quantitative approach, and it would be having four phases. So let's quickly walk through. For the research setting and the specific refrigeration units, it's located on IGA Express, Dayton, Ohio. This is similar to what we have here in the Philippines, such as Save More, retail supermarkets, and such the like. And for the condensing unit, it's the Emerson XFAM 050D TFC-081. This is a 5 HP condensing unit. And then the operating condition would be 25 degrees Fahrenheit on the evaporator and 120 Fahrenheit on the condenser side. So for the phase one, the selected sample would be from the temperature extremes found within the year for both seasons, summer and winter. So for summer, it would be August, and for winter, it would be December. So it shows the hottest in average for both temperature extremes. And for the analysis, based from the data logger that was logged from the probes in the store, so use from the Yokogawa MWM100, the data analyzer that we have used, we would be exporting the data into our computers, and then that would be converted into Excel format. So that would be the raw data. And then phase two of the analysis would be definition of parameters and variables, as you can see on the screen. So moving forward, suction line temperature would be designated as SLT, and discharge line temperature would be designated as DLT. And for the refrigeration setup and probe locations, you can see right here, the schematic on the left shows the setup on the store. The condensing unit is located on the roof. And then for the schematic on the right, you may see the pressure, temperature, and the current probes located in the system. And then the blue lines show the refrigerant line. So importation of the raw data tool. So as you may remember on the earlier phase, that would be inputted into the data compiler tool that I have created in order to compute the necessary calculations. to analyze the unit performance such as capacity, energy efficiency ratio, superheat, and other requirements needed for the calculation of the efficiency. And the formulas are embedded in the cells as shown. So after the data has been inputted on that tool, we expect this is the outputs as you can see on the figures on your screen. This will be explained on the later slides. Next, also we would be analyzing the extracted data through statistical analysis. So using multiple linear regression, we have two regression analysis that are conducted on the study. The predictor variables would be SLT, and another one would be capacity, and the response variables are shown on the table as you may see on the screen. So the method for multiple linear regression was conducted in the Minitab statistical software. So let us start on the results and discussion. First, we have the numerical results. For the SLT, average would be around 26 degrees Fahrenheit for the whole month. So that would be around just a difference of 1 degree Fahrenheit from the actual required operating evaporator temperature. So this is due to higher readings due to high ambient temperature. And also, if you may see, the SLT has high readings. These values are due to when the compressor is starting up. And also for capacity, as you can see here, average would be 36.5 BTU per hour, around 10.71 kilowatts. So it would amount to only 87% of the full product load, which is 41,700 BTUs per hour. And then that would be evidence of varying capacity because we were able to maintain the suction line temperature. Even though that we are only operating 87% of the capacity, we were able to maintain the average of 26 degrees Fahrenheit. So the capacity would be dependent on the mass flow. So more mass flow equals more capacity. And for the energy efficiency ratio, high EER values observed on average. So as you can see on the table on the right, it averaged around 9.5 for the month. So this were high EER values. So if you compare it to conventional energy efficiency ratios on conventional refrigeration units of around 3 to 5, this is higher in comparison. And also, we operated with higher EER as per the recommended values as well. So that is shows that the unit is running efficiently throughout the summer, even though we have high ambient temperatures. And for superheat, there are high readings, though normal readings on average, we have some instances wherein there's no superheat, so there are risks for a liquid refrigerant entering the compressor. But due to the compressor construction, we are fairly confident that the motor heat can able to vaporize the remaining liquid of the refrigerant vapor. So we will see on the later slides on the graphical section of the data. We will see it how it occurs, and it only occurred for a short amount of periods of time. And also discharge pressures were there are high readings on the discharge pressure. This is due to the high ambient temperature outside store, and it is directly relative to discharge line temperature. So this is the reason because we are operating on the summer extremes. Next. So for winter, average of 23 degrees Fahrenheit. So a difference of 2 degrees Fahrenheit. So it's much cooler than the required operating temperature. This is due to the low ambient temperatures experienced outside the store. And this is also lower compared to the SLT average in the summer. And basically for low ambient conditions, there's less effort for the unit to work the desired temperature, and low temperatures even when the compressor is unloaded. And for the capacity, it averaged around 32,400 BTUs per hours only. So 78% of the full product load. So again, this would be an evidence of varying capacity. We were able to maintain the suction line temperature, even though we have modulated the capacity of the unit. So why only 78% of the full product load? This could be a good evidence as well of the unit modulating on its required operation, because there is more load on the summer, much more heat infiltration inside the store because of higher ambient temperatures. So this can be due to the low ambient temperatures as well. So that is why it has lower capacity. And for the energy efficiency ratio, since lower ambient temperatures, less effort for the condensing unit to work the required temperature, we have logged an average of around 12 EER, so higher EER values compared to summer. And this is because, yeah, less effort for the system to work and much more efficient. And for the superheat, on the month of December, it experienced normal readings on average, so there are no any readings that are out of the ordinary or exceeded the recommended range. And now, let's start for the graphical results. Let's start for summer. Point A and B shows the high discharge temperatures. This is mainly due to ambient temperature. And point C shows the point before the compressor unloads because of the low suction line temperature, as you may see, and low discharge temperature. And interestingly enough, if you can see point D, majority of the points are parallel to the envelope. And this is the point wherein the compressor starts up. So mainly because of defrost cycles, and this is where the compressor starts, turns on, and then goes into point E. If you may see on your screen, that is where it points the operating range leads into. So point E would be the operating condition of the unit. So for the superheat, as you may see right here, there is liquid refrigerant entering the compressor based on negative or no degree superheat readings. As you can see right here, there are liquid slugging risks, but the compressor motor would be able to vaporize the liquid refrigerant before getting into the compression chamber, because based on how the compressor has been constructed, the liquid refrigerant will fall because of the density, will drop down into the motor, and then the heat of the motor would be able to absorb the refrigerant would be able to absorb the heat of the motor and then be vaporized and then go to the compression chamber. So that is good, because mainly that's why the compressor scroll has been designed that way, just to avoid these kinds of risks. And also, for the superheat, there was also high superheat readings for the month. And this one would be the suction line temperature versus the solenoid, unloader solenoid status. This was requested by Sir Ed. So as you can see right here, the SLT in the blue box has been modulated by the unloading sequence. So it was able to modulate and maintain the required temperature. And as you can see, it's also behaving as a pulse, like the solenoid, which is in a pulse width modulation form. It's also seen on the compressor amperage, the brown line, as you can see on your screen. It also acts, it behaves like a pulse width modulation, as same with the solenoid. So thus, current and also power would be lower in average, because on average, if you sum this up in a bigger picture, it would be there would be a lower power draw in the operation of the unit. So if you see the normal compression on the middle, there are higher demand for the power, and as you can see right there. And for the graphical results for winter, point F shows lower discharge line temperatures because of lower ambient temperatures experienced in winter, and lower DLT with the same SLT equals that would be much more efficient because of lower compression ratios. The unit is not working as much to maintain the operating condition. And for point G, this is new because if you compared it to summer, the whole operating points of the unit has been shifted to the left. So meaning it has less effort. The unit has less effort to um, cool down the refrigerated case. So the point G operating range shifted to the left, and this is where also similar to point H, the point before unloading occurs. And for point I, it would be also the compressor startup. So it only lasted a couple of seconds or so. And for winter, much more better readings in terms of superheat. No presence of liquid refrigerant entering the compressor. And then also it also experienced high superheats, but only a fraction of the time. And this would be the for the winter SLT versus the solenoid. So you can see similar to what is experienced in summer, but if you may compare it, the compressor amperage would be much more lower in comparison to summer. So let us start with statistical analysis. So for the first analysis would be suction line temperature versus discharge line temperature, ambient compressor power, and loader solenoid. And as you can see right there, multiple linear regression equation. As you can see from the equations, discharge line temperature positively impacts SLT. So same with the ambient temperature on summer. So it just mainly means that in summer, the higher the ambient temperature is, the higher the value of suction line temperature is. And based on this findings, we can say that DLT is also indirectly affected by the ambient temperature because in order for the heat to be transferred from the heat from inside the store or inside the unit or inside the refrigerated case to be transferred outside the ambient temperature, the DLT would need to be much higher than the ambient temperature in order to transfer heat from the environment. And as for winter, from hindsight, we can see the negative impact of ambient temperature. This can be due to the low temperature outside, and the unloader is the most significant on winter. That's why more unloading scenarios in winter. And there would be high difference on loaded and unloaded constant, if you can see right here. And for the compressor power on all equations, we can say that the compressor power negatively affects SLT. So because for a larger compressor power, it means the compressor is pumping refrigerant into the system. That's why the suction line temperature is much lower if the compressor power is higher. And for the Pareto chart, this shows which variables are the most significant. For Minitab, 1.96 is the cutoff point of statistical significance. And for summer, the most significant one would be the discharge line temperature, followed by the compressor power. This shows that the DLT or the ambient temperature affects greatly the value of the suction line temperature inside the case. And then power shows how the compressor is working much more harder in summer in compared to other months. And for winter, solenoid is much more prevalent. That would be term number D. This is because on the winter months, as you've seen before, it only has the capacity of 78%. So majority of the operation of the unit would be modulation. That's why the unload is the most significant effect on the value of SLT. And for the model summary, it only shows the predictability of the pattern. Um, for summer, it's much higher compared to winter because summer it's much more predictable in a sense. Because for the ambient temperature outside, it's much more stable in compared to winter because due to erratic ambient temperatures located in the winter because just a simple snowstorm would um, entirely affect the ambient readings outside the store. And for the second analysis, it would be capacity. And for the multiple linear regression equation, as you can see, discharge line temperature negatively impacts suction line temperature, and same as with the ambient temperature. And the higher the suction line temperature is, the higher the capacity of the unit. This is mainly because of the refrigerant density of the refrigerant inside the system. And for higher compressor power, we will expect higher capacity because more pump of the refrigerant, and then we much have more capacity as well. And for the Pareto chart, as you can see, for summer, compressor power is the most significant effect, while on winter, it's the SLT. For summer, the DLT or the ambient highly affects the summer readings for the capacity. It shows the indirect effect of the ambient temperatures through DLT. So as you can see, that would be an evidence of how it mainly affects the overall capacity of the system, especially for the ambient temperature, especially on hotter months. And for winter, suction line temperature would be the most significant because capacity is heavily reliant on the refrigerant density. So for suction line temperatures, a big change on suction line temperatures would mean a big um, effect on the value of capacity. And since majority of the operation of the unit is modulated, SLT is affected, and thus it reflects the value of the capacity. And it also shows the indirect effect of unloading on the capacity of the system because more unloading, more or less mass flow, the more the SLT is affected. And for the model summary, for the predictability of the pattern of values, higher predictability compared to SLT. Summer, again, much more predictable compared to winter because of erratic ambient temperatures. Okay, so for the conclusion and recommendation, the key takeaways on this study, refrigeration systems are very energy intensive. Improving efficiency is essential. This study evaluates digital unloading as a capacity modulation method. And digital unloading provides increased efficiency whilst having minimal components, less complex system offering, maintains required temperature at reduced power consumption. Condensing unit operated within approved operating envelope or range. And then results show that the ambient temperature's consistent influence on the SLT and capacity, whatever the season may be. Even though sometimes on summer, compressor power is the most relevant, but results show that ambient temperature has the consistent influence of the capacity of SLT and also capacity. Thus, unloading modulates mass flow. And with modulated mass flow, it affects capacity and temperature as well. So basically, the digital system is known in theory, but there are limited empirical analysis on the current study on the matter. That's why we have made this study as well. And also we made statistical validation on the relationships of the variables on the unit. And a couple of recommendations for future studies. There should be a baseline comparison between a modulated system versus an identical fixed capacity on-off system. We would be able to appreciate how much, or maybe we can see how much of a difference there is on the efficiency on a modulated unit, may it be digital, may it be variable speed, in comparison to um, a traditional on-off system. We would be able to appreciate how it differs in operation, and also how one is much more efficient than the other, given that it operates on identical conditions. And also, product loading changes should be tracked. Example would be store schedules, defrost schedules, maintenance schedules, as it affects the readings. And also additional sensors on the store may be door switch sensors, because the opening and closing of the doors on the reach-in case would affect the suction line temperature readings, especially due to air infiltration of the hot air entering the case. And then also voltage readers would be also helpful to um, have an exact reading on the power draw of the unit. And based on that additional parameters or additional variables, the use of other statistical models to define the relationship between the variables, because we are entirely limited to multiple linear regressions, given the limitations that we have in a study. It would definitely help to maybe use other statistical models to define the relationships of each and every variable that affects the suction line temperature or the capacity of the system. Okay, so that concludes my presentation, and I would be answering your questions. And yeah, see you on the 28th. Thank you, and see you soon.